So we've been talking about reactions, and we've talked about how the rate is affected. And so let's look at what happens if we have a reaction that's not just going one way, but that it can be reversible. And there's a lot of these that go on in the body and in industry as well. So a reversible reaction means that it can go in either direction. And so instead of just using the arrow going in one direction, you'll see this, or you'll see two arrows, one going left, one going right. And so what that means is it is an equilibrium reaction. That is, it's going both ways. And so what's interesting about these is, since they're reversible, I can do things to push it to go one way or to another way. And so when the forward reaction goes to the right, and then the reverse reaction goes back to the left. And when it's at equilibrium, the rate of the forward reaction is the same as the rate of the reverse reaction. So they're still going back and forth, but they're doing it at the same speed, basically. So in cells, this happens because cells are dynamic, they're not static. And so if a cell stops doing this equilibrium act, it dies. And so it's just going kind of back and forth, back and forth. The net concentrations, that is the changes basically of the reactants in the products, don't change at equilibrium. So you're really not making more or less of any one thing. It's just going back and forth, and it kind of evens out. So the relationship between the concentration of the products and the concentration of the reactants is what we call the constant, or the equilibrium constant, and that is signified by the letter K. Okay, the equilibrium constant. We put brackets around if we're going to talk about it's in concentration, and its concentrations in moles per liter. And so if I have this reaction, I have little a number of A, little b number of B, in equilibrium with little c numbers of C and little d numbers of D. I write the equilibrium constant K as the products. So this is the mole per liter, or molar concentration of the products divided by the reactants. But I have to take into consideration how many I have. And so the coefficient in the reaction becomes an exponent when I put it into this little formula here. So if I have the reaction of nitrogen gas plus oxygen gas giving me 2 moles of nitrogen oxide, the equilibrium constant for that would be the NO, because it's going to be products, because this is products, and these are the reactants. So my product is going to be the molar concentration of NO divided by the molar concentration of N2 times O2. And since these are ones, okay, then this is like raising them to the first power, which doesn't have any effect on it. But this one is a 2, so I have to put that to the second power, which basically is what? The same as squaring it. So the coefficient in the balanced chemical equations becomes the exponent in the equilibrium constant formula. So what K tells us is the reactant, or is the reaction going to be favored to go to the right or to the left? So let's think about what K is telling us. K is the product concentration divided by the reactant concentration. So if the numerator is larger, the products are bigger, then the equilibrium is going to favor the products. It's going to be going more towards the products because that number is higher. All right, so if they started out at 1 to 1 and then the products were 2 over 1, then you'd be making more products than reactants. That's basically what we're saying. If K is much less than 1, that is much less than 1, then the reactants are higher concentration than the products. The denominator this time is what is large, and so it will be favored to the left, which is favoring the reactants because they're what is higher concentration. So you have higher concentration of reactants. That means that the whole reaction is going towards the left, back towards the reactant. If the K is large, greater than 1, then that means that the products are higher concentration than the reactants, so it's moving towards the right. So when K is around 1, that means that your products and your reactants are both about the same, and so they are at equilibrium. Okay? All right. So an example of this is our H2 plus O2 giving us water. Okay? The K value, and this is from some table, okay? So some table where all of these are, K is 2.9 times 10 to the 82 times 10 to the 82. That is a big old number. So that means that since K is equal to the products over the reactants, if this number is big, that means this number is big. So that means that what? The products are going to be in higher concentration, so products are favored, and the equilibrium is going to lie to the right side. So it's going to be more towards this side than it is to the left. So in summarizing this in this table, if K is greater than 1, that means the products are bigger. And so equilibrium is favored to the products and it lies to the right. If K is less than 1, equilibrium is favoring the reactants and equilibrium lies to the left. If both of them are at equilibrium, then your K is going to be equal to 1. So if we're going to calculate K for the reaction, then we have to know the concentrations for the reactions. And so we need the reactants and the products. So if we're going to calculate K for the reaction between A2 and B2, the equilibrium constants are as follows. All right, so A2 is a 0.25 molar, B2 is 0.25 molar, and then AB is 0.5 molar. Okay? So when I write the equilibrium constant for K, I'm going to write products over reactants, and I'm going to have the coefficient become the exponent. So both of these are 1s, so anything raised to the first power is itself, so that's why I don't worry about that too much. So in this case, AB2, which is the AB squared, which is the product, divided by A times B. So then I just plug in those numbers. The concentration of AB was 0.5, and the concentration of A was 0.25, and B was 0.25. So 0.5 squared is 0.25, and 0.25 times 0.25 is 0.0625. And so when I divide those numbers, I get 4.0. And it's always molarity, so it's 4 molar. All right, so if it's 4.0, that means that K is greater than 1, which means this number was bigger, right, than this number. So the product was bigger, So I know K is greater than 1, so I can also say it's product favored and the equilibrium is more to the right.